that if a transmission line is terminated in its own characteristic impedance, then it produces no reflection. Okay, so if you have a scenario like this, what we talked before, a transmission line beta, if it is a parallel plate conductor or coax, whatever it is, if it has a natural impedance which is given by Z naught, which is square root of L over C, if it is terminated into its own characteristic impedance, or if it is infinitely long, let's say ZL is Z naught, in both cases you don't have any reflection. Okay, so the boundary condition is as such that at the point in space over here, let's call this Z equal to 0. Okay, Z is equal to 0, and what we see before was that if V by 0 over I by 0, let's say this transmission line has a characteristic impedance of Z naught, and let's say it's a lossless line, so K is real. If it was a lossy line, then K is imaginary. Okay, I mean if it has some a dielectric filling, or if it is you're considering the finite resistivity of metal conductors, then there's some loss. So K the propagation constant K becomes imaginary. Okay, so at the point this we are talking of at Z equal to 0, at the point where the load is attached. Okay, so if this is equal to Z naught, if it matches with the characteristic impedance of the transmission line, then there is no reflection. Okay, so all the power is transmitted down the line to the load. Okay, so there is no problem for reflection. But if ZL is not equal to Z naught, and V0 by V of 0 divided by I of 0 is different, it's some arbitrary load GL, let's say it's not equal to Z naught, then we have reflection. Okay, so and what we did was we calculated the reflection coefficient gamma. As such, we considered V0 by I0, and we said that the gamma, when you have this Z naught different from well, when ZL is different from Z naught, then you have the reflected wave VR, so the ratio of reflected wave to the incident wave, let's call this VF. Okay, so let's say this V plus denotes an incident wave, this is reflected wave, so gamma is non-zero quantity. And another thing to infer from this discussion of gamma, the reflection coefficient, is that the magnitude of gamma can be complex. Okay, but gamma can never be greater than 1. Okay, why is that? Why we can't have gamma greater than 1? Well, you understand that you cannot have the power reflection, you cannot have a power that can be reflected back more as compared to what is being transmitted. Okay, so there's always a fraction because of impedance mismatch. There will be some fraction of the power that is being reflected back. So this ratio is less than or equal to 1. Okay, or precisely if we say the magnitude, the reflection coefficient magnitude. Okay, so this is less than or equal to 1. So the ratio is less than 1. So this gamma, if you recall, at Z equal to 0, we calculated that Z equal to 0 in terms of the impedances. That is, this is okay. This is ZL, and ZL minus Z naught, ZL plus Z naught. So what we did was we calculated this from considering V naught by I naught, and this was equal to ZL. Okay, so if over here you see in this equation you have V0, V of 0 equals to, you see this is 1 plus gamma. Okay, and then over here in the second equation for I naught at Z equal to 0, we have this is equal to 1 minus gamma whole divided by Z naught, the characteristic impedance of the line. And if you take the ratio of these two equations, okay, this is the first equation and this is my second equation. So equation 1 divided by equation 2 yields the following result here. And if you make the gamma the subject of this formulation, well, we have this this expression for the reflection coefficient, and that is at Z equal to 0. Okay, why is it at Z equal to 0? Because we are calculating this at the ratio of the voltage to current is being calculated at Z equal to 0. So, but then again, this gamma at 0, you see, as the transmission line impedance is modified, if ZL is different from Z naught, and that is your Z prime. Let's say this is the input impedance of the line. So down the transmission line, which is having a physical length of small l, and electrical length of KL, K being the propagation constant. So this KL is the electrical length of the line. Okay, call it EL, whatever you want to say. So this is the electrical length of the line, and this is the phase difference that the line imparts. So based on this small l or KL electrical length, you have the impedance transformation, okay, and that's in terms of Z naught ZL. And we discussed that how short circuit, open circuit condition, and arbitrary inductive or capacitive load conditions, they change the impedance down the line as a function of small length L or the electrical length. Now, it also turns out that if gamma can be expressed in terms of uh, the impedance in terms of ZL and Z naught, at gamma can be expressed at Z equal to 0 in terms of the load impedances and the characteristic impedances, then gamma, what is gamma at, let's say, KL? Okay, so what is gamma at KL? Well, for that you need to go down the line, okay, and you need to reach at minus L and see what is gamma KL, or what is gamma, let's say, uh, halfway between the over the transmission line KL by 2. And well, it's not very hard to come up with a general formulation of gamma, just like the transformed impedance. This is the transformed impedance. So what about the transformed gamma? Okay, transformed gamma, you see, if you recall the basic definition, that is the reflected part divided by the incident part. So if I'm going to put this as, okay, I'm going to make this a function of Z first of all, okay, because I understand the gamma, and which is indeed the case. Gamma is the reflection coefficient is going to change down the line wherever you are in terms of space coordinate Z. So this is given by the reflected wave, which is, let's call this gamma. This gamma is gamma of 0. So I'm going to write this as gamma 0. This is at Z equal to 0. Then we have E, J, K, Z. That's my reflected part of the voltage waveform. Divided by, I have the incident part, that is E minus JKZ. So E minus, I'm calculating the just like impedance transformation, I'm calculating the reflection coefficient transmission down the line. Okay, the function of Z. So my gamma is a function of Z. It turns out it reduces to gamma 0. Okay, that is at Z equal to 0 into E, simply E J twice KZ. Okay, and if I'm interested to find, just like over here, this Z prime is at this Z prime you are looking over here, and you are just at the other end of the line. So the electrical length is KL. Okay, electrical length is KL, or which means Z equal to, Z is minus L over here. Okay, if your origin is at the load side, okay, this is the this is equal to 0. So down there you have to go to Z minus L. You traverse the line all the way down to Z equal to minus L, which is the physical length. So just like this, what we do is, in terms of Z equal to minus L, if I replace this by minus L, well, this is my reflection coefficient. It turns out to be gamma equal to 0 into E minus J 2 KL. Okay. The thing is, if I have if Z equal to 0, you see, if Z equal to 0 over here, then this E of 0 is 1. Okay, so we are left with gamma Z equal to 0 is gamma 0, which is right over here, right? And because we evaluated this at Z equal to 0, right? So we get the same expression. So this is my gamma equal to 0, right? But then since the gamma and your impedance, the load impedance and the characteristic impedance, they are just like a one-to-one mapping. So you can, if you make the gamma the subject of formulation in terms of the load impedance and the characteristic impedance, you can make the impedance as a load impedance as a subject of formulation in terms of gamma. So gamma and Z are interchangeable. Okay, so uh, why we need the transformation of gamma, and why it is customary to or it is popular approach among microwave and antenna engineers to consider gamma, is that there are certain advantages. Uh, why we don't prefer to look at the impedance transformation. We don't look impedance as a function of the transmission line electrical length, how it is being transformed due to the load impedance different from Z naught. In preference to that, the preferred choice is that we look at the reflection coefficient transformation. Okay, and that is as such, it offers some advantages. So what advantages that we are going to look very quickly. Okay, so what we have said is that if the impedance produces a reflection coefficient, okay, which is given by gamma 0 ZL minus Z naught ZL plus Z naught, then this relation can be easily inverted in terms of Z equal to Z naught 1 plus gamma 1 minus gamma. So there is a one-to-one mapping between Z and gamma. So what this is exactly what we have seen before. So there is a, you can take this Z over here. Okay, so either you can have this load impedance in terms of gamma, okay, or you can have gamma in terms of load and characteristic impedances. So there's a one-to-one mapping. Now this is real. So in antenna and microwave work, especially when you are using S parameter analysis, it is customary to think in terms of gamma. So gamma is a preferred choice rather than Z. If you're going to look down the line and you want to, have the you want to know what is the impedance that is being transformed at, let's say, quarter wavelength or half the wavelength. Well, you can carry out this calculation from the gamma itself, right? Because gamma and Z, they have a one-to-one correspondence. They have one-to-one mapping. So if you know what is reflection coefficient at, let's say, Z equal to half the wavelength, or whatever the electrical length is you are interested, if you know what is gamma, you can find what Z is. Okay, so there's a one-to-one mapping that exists. So why do we need gamma? So let's have a look. So one big advantage of working in the complex gamma plane is that the modification of an impedance represented by equivalent gamma is extremely simple. The reflection coefficient for the given impedance as seen through the length of the line is just gamma E minus J2KL. And what it means is that we simply rotate the point clockwise, okay, just like a phasor we do in the time domain E, J, omega t. So we rotate the point clockwise from the origin. Gamma equal to 0 implies, what does gamma equal to 0 implies in terms of impedance? It implies ZL is Z naught, isn't that right? If ZL is equal to Z naught, then there's no reflection, okay, or reflection coefficient is 0. So what it means is that from the origin, you're going to rotate clockwise by an angle 2KL, which is twice the electrical length of the transmission line, to give the modified gamma prime, which is your reflection coefficient, okay, and this reflection coefficient is precisely at Z equal to minus L, okay, Z equal to minus L. So the modified reflection coefficient. So while we're rotating this, the idea is, you see, this is easy to see, that we add a length of the cable because the incident wave phase is delayed by KL getting to the end of the cable, and the reflected wave is delayed by the same electrical length getting back again. So the effect of the cable is therefore to rotate the complex number gamma clockwise by an angle 2KL. So the thing is, on a transmission line, the incident wave from minus L to 0 is equal to 0, which is equal to minus L, is going to, the forward wave is going to suffer a phase delay of KL, okay, traveling towards the load. Then when ZL is not equal to Z naught and the reflection, there's a certain reflection coefficient, so there's a transmitted wave, it's again going to suffer another phase delay of KL. So the round trip is 2KL, okay, KL plus KL is 2KL. So that is exactly what is happening over here. So you have 2KL of phase difference, okay. So if you're going to add a length of the cable, the incident wave phase is to be delayed by KL. It is getting to the end of the cable. The reflected wave is delayed by same KL getting back again. So the effect of cable is therefore to rotate So what you're doing is you're rotating the complex number, okay, gamma clockwise by an angle 2kl. I mean, if you have to find the reflection coefficient down the line at any arbitrary point, whatever the electrical length you want to find it at, be it 3 lambda by 2 or lambda by 6 or whatever it is, just substitute that for z over here and you find the reflection coefficient, and you know what gamma 0 is at z equal to 0. So basically that's the story, and you can find from gamma, you can find the impedance as well. So you are rotating the phasor. It's just like phasor, so you're rotating it clockwise, okay, by an angle 2kl. So just keep in mind that gamma plane is a complex plane, but it's not like an Argand's diagram, okay? So it's not the simply a diagram in which you have the real and imaginary parts, a complex plane like S plane, or like um, a complex variable plane which has real and imaginary parts. So there is a difference, and we're going to look at it. You see, but before that, let's consider some few special points for the gamma plane. You see, for the first thing is the center of the plane, what we discussed before, gamma equal to 0. It corresponds to the reflected wave of 0 amplitude. Isn't that right? Because gamma, by definition, is V reflected. Okay, that's our minus sign to show its direction. Then we have the incident, which is forward traveling wave, plus, and if it is 0, that means, what it means is that you have a matched condition. So basically this is implying that your reflected wave is 0 due to ZL being equal to Z naught. Okay, so your origin on the gamma plane, ZL, the origin for gamma equal to 0 is Z naught. Okay, that's transformation from gamma to Z. So this implies this is gamma equal to 0, or the origin of the complex plane, gamma plane. Gamma equal to 0 corresponds to the reflected wave of 0 amplitude. So this point represents the impedance Z naught plus J0. Okay, so this is your imaginary gamma, this is real gamma. Gamma is a complex quantity. Okay, it has a magnitude, and then it has a phase. So let's say E J theta, theta being the reflection coefficient angle phase. And if you're going to look at the real and imaginary parts, so you see at here the point, this is your origin, gamma equal to 0. Okay, that's 0 plus 0j, and this corresponds to the impedance of Z equal to Z naught. Okay, so this is your origin. That's the first thing to look at, and you can see it from here as well. If ZL is equal to Z naught, then this gamma is equal to 0. Okay, then the other thing is the magnitude of gamma, the radius from the origin, must be less than or equal to unity for passive impedances. Otherwise, the reflected wave would have more power than the incident wave. So this is what we have talked before as well. You see, this ratio can't be VR by VF. This can't be greater than 1. So do you understand that? You see, it can't be greater than equal to. It has to be less than 1. So this is not true. Why? Because you cannot have a reflected power that is greater than the incident power. Okay, due to the mismatch, there will be some power that is going to reflect back. You see, for an infinite standing wave ratio, okay, fine. For infinite standing wave ratio, there is no transmission being done. So the transmission S parameter will be small because all the wave is being reflected back. So you don't have much transmission, but it can't be greater than, again, it can't be greater than the forward wave. So it implies that the magnitude of gamma is less than or equal to 1. Okay, you cannot have reflected power more than the incident power. So due to that, you see there is the limiting circle is gamma equal to 1. Okay, gamma equal to 1 is the limiting circle, and the point on this circle, minus 1 plus J0, this corresponds to a short circuit. Okay, you see, at Z equal to 0 in this expression, if you are going to evaluate the expression at ZL short circuit condition, which is 0, this comes out to be minus 1. Okay, exactly minus 1. So where is the short circuit? Let's locate that. So you see the real part is minus 1. There's no imaginary part, so we are here, and we have a short circuit here. So this point was equal to 0. Okay, so you see with the gamma we have the impedance transformation as well. So there is a one-to-one mapping. So you must understand from the complex gamma plane how you are transforming between z and gamma. Okay, so what does gamma? If you are going to specify gamma, well, you can specify the z as well. So this point is your natural impedance of the transmission line. This point, for example, shows a short circuit. So gamma equal to minus 1 shows a short circuit. Uh, minus 1 basically means that your reflected wave is minus Vf. So all the incident power is reflected back due to the severe impedance mismatch. And then similarly you have for open circuit conditions, if ZL is infinity, then that's the open circuit. So if you have a case for infinity over here, what you do is you divide this by ZL, the numerator and denominator, so this is 1 divided by ZL, okay, and this also divides by ZL basically, and this is equal to 1 minus this is 1, so this will be, this ratio is 0, this is 0 because ZL is very large, and this becomes equal to plus 1, and so this is plus 1 plus J0, and this corresponds to open circuit conditions for ZL, right? So gamma equal to 1 plus J0 correspond to the open circuit. So you see from the open circuit conditions or load of infinity, if we are going to move down the circle of the unit circle, this is a unit circle of magnitude equal to 1, so the radius is 1. This is short circuit conditions. Okay, for infinity, if you're moving down the real axis, this is the real axis. Okay, so that's the maximum load impedance that you can have. Okay, and then this is the minimum load impedance that you can have, and both the points are on the unit circle. Okay, circle of radius equal to 1, gamma equal to 1. Then the points, the fifth point is that the points on the unit circle are gamma equal to 1, magnitude of gamma equal to 1. They correspond to pure reactance. Okay, pure reactance means there is no real part. All the points, however, all the points inside the circle, they map to the impedance with positive or non-zero R. The thing is, you see, if you're going to look at this expression again, well, it's too messy, but don't mind. Let's write this down again. So we have ZL minus Z0 over ZL plus Z0. So at what it says is the points on the gamma equal to 1 circle, they don't have the real part. They don't have the real part. The reason is, you see over here, the real part is they are pure reactances. Okay, it implies pure reactance in terms of the impedance. So all points inside they map to the impedance with positive non-zero R. So if you have z equal to 0 plus jx, so ZL, the load impedance is of the form which is either inductive or pure capacitive. So let's say jx. If you're going to substitute this for jx, then we have jx minus z0 over jx plus z0. Okay, so you see that I won't say that this is conjugate of each other, but if you're going to take the magnitude, this side of the equation and the other side of the equation, that's equal to 1, isn't that right? Because x squared plus z0 squared and square root, or x squared z0 squared in the denominator, square root of that, it's going to cancel out. Okay, so the magnitude is still 1. Magnitude is 1, but the phase is not necessarily equal to 0 over here. So phase could be anything. But again, what the point means is that if you're moving on the circle of radius equal to 1, okay, so this is your circle of gamma equal to 1, that implies pure reactance. Okay, that implies purely reactive load. That implies on this circle your ZL the load at which the transmission line is terminated is purely imaginary. It's form of Jx. Okay, depending on if x is negative or positive, it is capacitive or inductive. Well, that's another qualification. We are going to look at that point as well. But it's purely reactive. There is no real part. See, if it had to be a real part over here, then that will be, for example, r minus z naught and r plus z naught. It will be something else. Okay, so the magnitude won't be equal to 1. It won't be equal to 1. So on the unit magnitude gamma circle, you have pure reactance in terms of the load impedance. Okay, so then the sixth point is that if gamma is equal to J1, then this corresponds to an inductance. Okay, which means Z equal to 0 plus JZ0. So you see, if that is the case, if you have an inductive load, okay, JZ0, then JZ0 minus Z0 over JZ0 plus Z0, that should be equal to, the magnitude of this is equal to 1 again. Isn't that, you see, this is J minus 1, then you have J plus 1. So again, the magnitude is equal to 1. Magnitude, they're going to cancel out this. So it's 1. So all the points in the top half of the gamma plane, you see, since gamma equal to 1 corresponds to the pure reactance, and if you're going to bifurcate the circle in two semicircles, so for example, if you have this, the upper half of the gamma equal to 1 circle is pure inductive, because we are moving on the reactance, and reactance could be inductive or capacitive. So the upper half of the circle of gamma equal to 1 is purely inductive. This is inductive. This is inductance. Okay, there is an inductive load over here. This implies inductance. Similarly, if you have the lower part of the gamma equal to 1 circle, so what it says is all the points at the top of the gamma plane are inductive. They are of the form r plus jx, because you see a positive sign over here. Or equivalently, in terms of admittance, we are taking the reciprocal, so this is minus over here. Okay. Similarly, for gamma equal to 0 minus j1, gamma equal to 0 minus j1 corresponds to 0 minus jz0, and that implies all the points in the bottom of the gamma plane are capacitive. Okay, so this part is capacitive. This part is capacitive. So let's see at the next diagram of the gamma plane, complex gamma plane, where how it is located. So you see, this part is inductive, this part is inductive, this part is capacitive. Okay, so you see over here, for example, gamma 0 minus j1, where is it? This is capacitive, because you see at the load impedance is minus j0, so this is capacitive load. Okay, and it occurs in the semicircle, that is the lower half, in the lower half portion of the complex gamma plane, and the upper half semicircle, if you consider, or the upper half of the gamma plane, you consider the load impedances. This is 0 plus j1. Okay, so there is a difference. This is inductive. This part is your inductive. This is inductive. So x over here is greater than 0, or should I say gx is greater than 0. Then in this part, the lower part, g of x is less than 0, so that's capacitive. Okay, look at this point, for example. Okay, and then on the real axis, from infinity to 0, you have in open circuit to short circuit conditions. That's the idea. How you, the first thing is that if you remember that there is a one-to-one mapping between z and gamma, then if gamma is specified, you can find out what z is wherever you are on the transmission line, and or from z you can find the gamma likewise. So on the gamma plane, you know how the plane bifurcates itself into inductive and capacitive loads, and what does it mean by a short circuit, open circuit, in terms of the gammas, how gamma reflects the short circuit conditions or the open circuit condition, and how they reflect the inductive load conditions, okay, the capacitive load conditions, okay. what does gamma equal to 1 circle mean. So basically these points are easily verifiable if you know how to calculate gamma and what does gamma means. Okay, so it's not very hard to see what it.